have any hope of finding alien life, we have to know what to look for. But where do we begin? How do we narrow down a seemingly infinite set of possibilities? There's one thing we know for sure. Nature will have to play by her own rules. No matter how strange alien life might be, it's going to be limited by the same physical and chemical laws that we are. On top of this, each alien environment will further limit what kinds of life forms can evolve there. Despite these natural boundaries, the possibilities are staggering to imagine. Trillions of planets, each a unique cauldron of chemicals undergoing their own complex evolution. To guide our thinking, this museum of alien life will be divided into two exhibits. Life as we know it, home to beings with biochemistries like ours, and life as we don't know it, home to beings that challenge our concept of life itself. Before we venture too far into the unknown, we have to ask ourselves, what if alien life is more like us than we think? If there's one feature that unites us with the other specimens in this museum, it's carbon.
Carbon is ubiquitous. It's one of the most common elements in the universe, and it's very good at forming large, stable molecules.
Carbon has the rare ability to form four-way bonds with other elements and to bind to itself in long, stable chains, enabling the formation of huge, complex molecules. This versatility makes carbon the centerpiece in the molecular machinery of life. And the same carbon compounds that we use have been found far from Earth, clinging to meteorites, and floating in far-off clouds of cosmic dust. The building blocks of life, drifting like snow through the universe. And if alien life has selected other carbon compounds for their biochemistry, they will have plenty to choose from. Scientists recently identified over 1 million possible alternatives to DNA, all carbon-based. If we ever discover other carbon-based life forms, we would be fundamentally related. They would be our cosmic brethren. But would they look anything like us? If they hail from Earth-like planets, we could share even more in common than just our biochemistry.
What would life be like on other planets if it has evolved? Would it be like the world today here on Earth? Or would it be completely different? There are those who argue that from the argument of convergent evolution, if conditions on other planets are similar to here, then we would see very similar life forms. Animal and plant-like organisms that look very familiar.
certain features like eyesight, echolocation, and flight have evolved multiple times independently in different species. This process of convergent evolution could extend to alien planets like Earth, where creatures face similar environmental pressures. It's no guarantee, but there could be certain universalities of life. The greatest hits of evolution on repeat across the universe. Each feature would be attuned to its local environment. Dimly lit planets would produce huge eyes to suck in extra light, like nocturnal mammals.
Some people have gone so far as to say that human-type organism, humanoids, will occur on other planets.
The existence of other human-like organisms seems unlikely, given the long, convoluted chain of events that produced us. But we can't rule it out. If just one in every 100 trillion Earth-like planets produced a human-like form, there could still be thousands of creatures like us out there. Convergent evolution is also rampant in plant life, and C4 photosynthesis has arisen independently over 40 times. Would alien plants look like ours or something else entirely? On Earth, plants appear green because they absorb the other wavelengths in the sun's light spectrum. But stars come in many colors. And alien plants would evolve different pigments to adapt to their sun's unique spectrum. Plants feeding off hotter stars could appear redder by absorbing their energy-rich bluer light. Around dim red dwarf stars, vegetation could appear black, adapted to absorb all visible wavelengths of light. Earth itself may have once appeared purple due to a pigment called retinol that was an early precursor to chlorophyll. Some think that retinol's molecular simplicity could make it a more universal pigment. If so, we may find that purple is life's favorite color. Vegetation is more than just a curiosity. It's chemical information that could be seen from light years away. Earth plants leave a signature bump in the light reflected off our planet. Finding a similar signal from another world could point the way to alien vegetation. Perhaps this will be our first glimpse at alien life, a vibrant hue cast by a distant world.
What happens when you change the day length of a planet? What happens when you change the tilt of a planet? What happens when you change the shape of the orbit? What happens when you change the gravity of a planet?
Planets with long elliptical orbits would see drastic seasons. There could be worlds that appear dead for thousands of years, then suddenly spring to life. Most of the rocky planets discovered so far have been massive super-Earths. How would life evolve on these worlds? In the seas, gravity may not matter much at all.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity.
High G-forces would necessitate large bones and muscle mass in complex life on land. They would also demand a more robust circulatory system. And plant life could be stunted by the energy cost of carrying nutrients under stronger gravity. Low-gravity planets would more easily lose their atmospheres to space and lack a magnetic field to protect from cosmic rays. But smaller worlds could be home to secret oases. Huge cave systems that provide hideouts for life. Possible habitable planets are estimated at 2.5% Earth's mass. If surface life does evolve on these worlds, it could be a sight to behold. Plant life could grow to towering heights, able to carry nutrients higher in lesser gravity. Without the need for bulky skeletons and muscle mass, animals could have body types that boggle the mind. Here on Earth, it took 3 billion years for evolution to produce complex plant and animal life. Simpler organisms are hardier, more adaptable, and more widespread. The largest collection in the Museum of Alien Life would likely be the Hall of Microbes. Yet finding even the tiniest alien microbe would be a profound discovery. and bite-sized life could leave a big footprint. Like stromatolites on Earth, layers of microbes could build up into huge rock mounds over time, leaving behind eerie structures. And in big enough numbers, some alien bacteria could leave a distinct biosignature by exhaling gases that wouldn't coexist naturally, like oxygen and methane.
There's ways to make oxygen without life, there's ways to make methane without life, but to have them in the atmosphere together is almost impossible unless you've got biology making those gases at the surface. And it would have an imprint on the planet's spectrum of colors.
Next generation space telescopes could find a signal like this on a world not far from home.
The closest sun-like star with an Earth-like exoplanet in the habitable zone is probably only 20 light years away and can be seen with the naked eye.
Most brown dwarfs are too hot to support life as we know it, but some are just cold enough. All the prime elements for life have been detected inside their atmospheres. And within these clouds, some layers would provide ideal temperatures and pressures for habitability. There could be photosynthetic plankton in these skies, kept aloft by churning upwinds. And with enough force, these upwinds could even support larger, more complex life. Predators. This raises a crucial question. What if we've been looking in all the wrong places? What if nature has other ideas? Most of the universe is too cold or too hot for liquid water and the biochemistry that supports life as we know it. But in case our biases are misleading, we have to cast a wide net to search for life outside the habitable zone, in places that seem wildly hostile to us. Exotic environments will demand exotic biochemistries, and while no element can match carbon's versatility, one contender is a frontrunner. At first glance, silicon seems similar to carbon. It forms the same four-way bonds and is also abundant in the universe. But a closer look reveals that these two elements are false twins. Silicon bonds are weaker and less prone to forming large, complex molecules. Despite this, they can withstand a wider range of temperatures, opening up intriguing possibilities.
Life based on the silicon atom instead of carbon would be more resistant to the extreme cold, providing a whole new range of weird forms.
But silicon has a problem. In the presence of oxygen, it binds into solid rock. To avoid turning to stone, silicon beings might be confined to oxygen-free environments, like Saturn's frigid moon, Titan. Its vast lakes of liquid methane and ethane could be an ideal medium for silicon-based life or other radical biochemistries. Without ample sunlight, beings on worlds like Titan would likely be chemosynthetic, deriving their energy by breaking down rocks. Such life forms could have ultra-slow metabolisms and life cycles measured in millions of years. In high temperatures, typically rigid silicon-oxygen bonds become more flexible and reactive, triggering more dynamic chemistry. This has led to a truly bizarre proposal: silicon-based life forms that live inside molten silicate rock. In theory, these forms could even exist deep beneath the Earth inside magma chambers as part of a shadow biosphere. If so, then the aliens are right under our noses. Other shadow biospheres have been proposed, forms of life living alongside us that we don't even know are here, including tiny RNA-based life small enough to go undetected by existing instruments. Clouds of dust in empty space might seem like the last place you'd expect to find anything living. But when cosmic dust makes contact with plasma, a type of ionized gas, something strange happens. In simulated conditions, dust particles have been seen spontaneously self-organizing into helical structures that resemble DNA. These plasma crystals even begin to exhibit lifelike behavior, replicating, evolving into more stable forms, and passing on information. Plasma is the most common state of matter in the universe. If complex evolving plasma crystals really exist, and if they can be considered life, they could be its most common form. massive suns explode, some collapse into ultra-dense cores called neutron stars. Hulking masses of atomic nuclei crammed together like sardines. Conditions on the surface are mind-boggling. Gravity is 100 billion times stronger than Earth's. But beneath their iron nuclei crust lies something strange. A hot, dense sea of neutrons and subatomic particles. Stripped of their electron shells, these nuclei would obey entirely different laws of chemistry, based not on the electromagnetic force, but the strong nuclear force which binds nuclei together. In theory, these particles could link up to form larger macronuclei, which could then combine into even bigger supernuclei. If so, then this bewildering environment would mimic the basic conditions for life: heavy nucleon molecules floating in a complex particle ocean. Some scientists have proposed the unimaginable: exotic life forms drifting through this strange particle sea, living, evolving, and dying on incomprehensibly fast timescales. Life is not something that has to evolve naturally. It can be designed. And once intelligence is introduced into the evolutionary process, a Pandora's box is opened. Typical biological limitations, synthetic and machine-based life could be the most successful of all. It could thrive almost anywhere, including the vacuum of space, opening up vast frontiers unavailable to biological organisms. And compared to the glacial pace of natural selection, technological evolution allows exponentially faster growth, adaptability, and resilience. By some estimates, autonomous self-replicating machines could colonize an entire galaxy in as little as 1 million years. Can't predict how hyper-intelligent life would organize itself. But in theory, there could be convergent evolution at play. The electrical properties of silicon might make it a universal basis for machine intelligence, a redemption for its biological shortcomings. ages, perhaps machine intelligence will come to dominate, and naturally occurring biological life will be viewed as a quaint starting point. Perhaps we ourselves will lead this transition, and the great human experiment will be merely a first link in a sprawling intergalactic chain of life.
Has said that one does not meet oneself until one catches the reflection from an eye other than human. One day that eye may be that of an intelligent alien. And the sooner we eschew our narrow view of evolution, the sooner we can truly explore our ultimate origins and destinations.